A very good afternoon to one and all present here. I, ICRTCS, Assistant Professor, Department of Information Science and Engineering, Vidyavardhaka College of Engineering, would like to welcome you all for the AICTE-sponsored Second International Colloquium on Recent Trends in Computer Science, ICRTCS 2021, for the topic on exploiting machine learning for improving in-memory execution of data-intensive workflows. I would like to welcome our Honorable Principal, Dr. B. Sitashive Gowda, for this session. Welcome you, sir. I'd also like to welcome Dr. Ravi Kumar V., Professor and Head, Department of CSE, VVCE Mysuru. Welcome you, sir. I also welcome Dr. Gururaj HL and Dr. Janvi V., Associate Professors and Wing Coordinators, Department of CSE, VVCE, for this session. Welcome you, sir, and welcome you, ma'am. I take this opportunity. Thank you, sir. I take this opportunity to welcome today's keynote speaker, Dr. Paolo Trunfio, Associate Professor in the Department of Computer Engineering, University of Calabria, Italy. Welcome you, sir.
Thank you.
I also extend a hearty welcome to all the participants. Welcome you all. Moving on, it gives me an immense pleasure to introduce today's speaker, Dr. Paolo Trunfio, to this gathering. Dr. Paolo Trunfio is an Associate Professor of Computer Engineering at Dimes Department, University of Calabria, Italy. He is also a co-founder and a Managing Director of DTalk Lab SRI, an academic spin-off of the University of Calabria. He has published many scientific works, including 3 books, namely Data Analysis in the Cloud, Service-Oriented Distributed Knowledge Discovery, and Internet of Things based on Smart Objects, Technology, Middleware, and Applications. He has served as a PC Vice Chair of the 27th Conference on Advanced Information, Networking and Applications at Spain. Sir is also a local organizer for the 3rd COST 804 Training School on Energy Efficiency in Large-Scale Distribution Systems at Italy. He was also the PC Chair of the 7th International Workshop on Peer-to-Peer Architectures, Networks and Systems at Italy. He has also contributed as a scientific coordinator for the 2nd NESUS Winter School and PhD Symposium 2017 at Italy. He was also a part of track chair of the 6th International Conference on Emerging Internet, Data and Web Technologies at Albania in the year 2018. Sir is serving as an associate editor of the IEEE Transactions on Cloud Computing, advisory board member of the European Conference on Parallel Computing, editor of the International Journal of Web Science, and is also a member of editorial board of several scientific journals, including Future Generation Computer System, Peer-to-Peer Networking and Applications, and the Journal of Big Data. It is a total privilege and honor to have you today as our speaker, sir. I now request Dr. Paolo to take over this session. Thank you, sir.
Thank you so much for your kind introduction. I'm going to share again my presentation, just 1 second. Okay, I hope you see my screen now. I'm not sure, but...
Yes, it is visible.
Okay, thanks.
Thank you.
So first of all, good morning. Thank you for the nice introduction. First of all, I would like to thank all the organizers, so the chief patrons, the wing coordinators, the colloquium coordinators, and all the members of the organizing committee for the kind invitation, and also all the colleagues who are attending this talk. This presentation will describe a novel solution called the Intelligent In-Memory Workflow Manager, IIWM, for optimizing the in-memory execution of data-intensive workflows on parallel machines. Let's start from some motivations and goals of this work. A data-intensive workflow is a process that usually involves a set of computational steps implementing complex scientific functions, which can include the data acquisition, data transformation, data analysis, storing data somewhere, and visualizing results. Parallelism can be achieved by concurrently executing independent tasks by trying to make use of all computing nodes so all the processors available, all the servers in the systems, even if in many cases it is necessary to execute multiple tasks on the same computing node. For example, this occurs when the number of tasks is greater than the number of available nodes, or because multiple tasks use a dataset that is located on the same node. Of course, these scenarios are prone to memory saturation, and moving data to disk may result in higher execution times, which leads to the need for a scheduling strategy which is able to cope with this issue. For these reasons, we need to adopt optimization techniques that are able to fully exploit in-memory processing, avoiding the performance drop that we can encounter when memory saturation events occur. In most cases, distributed processing systems use a priori policies for handling task execution and data management. For example, we have two important examples of data processing systems, which are MapReduce, the MapReduce programming model made popular by Hadoop, and the Spark system, which on the other hand is based on the DAG model, so direct acyclic graph programming. In the case of MapReduce and Hadoop, there are so-called mappers, which write intermediate results after each computation. So performing disk-based processing with partial use of memory through the exploitation of the so-called Hadoop distributed file system, which is also called HDFS with using the acronym, of course. On the other hand, Apache Spark, which can be considered the state-of-the-art data analysis framework for large-scale data processing, exploiting in-memory computation, relies on the DAG paradigm and is based on some abstractions which make computation much more efficient than the computation made by Hadoop. This is in particular obtained by using the so-called RDD model, which is a distributed memory abstraction for keeping data distributed over a set of nodes, which enables parallel computation. In general, as I said before, the Spark in-memory approach is considered more efficient. But even in this system, we can have a time overhead that is caused by spilling data from memory to disk when memory usage exceeds a given threshold. This overhead can be significantly reduced if the memory occupancy of a task is known in advance. This is important because we can avoid running in parallel two or more tasks that cumulatively exceed the available memory, thus causing data spilling. For this reason, memory is considered a key factor for the performance and stability of Spark jobs, and OOM errors, so out-of-memory errors, are often hard to fix. Recent efforts have been oriented towards developing prediction models for the performance estimation of big data applications, but most of the approaches rely on analytical models, and only a few recent studies have investigated the use of supervised machine learning models. In this presentation, I'm going to propose a novel solution. As I said before, it is called the Intelligent In-Memory Workflow Manager, or IIWM, which is for optimizing the in-memory execution of data-intensive workflows on parallel machines. The proposed system is based on two components. The first is a regressor, which exploits a machine learning strategy for predicting the memory occupancy and execution time of workflow tasks. The second component is a scheduler, which allocates tasks to a computing node, taking into account the predicted memory occupancy made by the aggressor and the execution time of each task and memory available on that node. The proposed solution is designed around two main assumptions. The first is that the underlying HPC platform is homogeneous, which means it is composed of many identical servers having the same architecture, processor type, operating system, and so on. And the second assumption is that all the tasks are known in advance and the task set is not modifiable at runtime. So in practice, I'm saying this is a kind of a static scheduling approach. Recent studies have shown the effectiveness of machine learning-based prediction modeling in supporting code optimization, parallelism mapping, resource allocation, and so on. In addition, predicting running times and memory footprint is important for estimating the cost of execution and better managing resources at runtime. State-of-the-art techniques aimed at improving the performance of data-intensive applications can be divided into two main categories that are analytical-based and machine learning-based. In analytical-based systems, information collected at runtime and statistics are used for performance improvement. Typically, the systems are easy to implement and they can be executed with relatively low computational cost, but they require continuous monitoring and lack a prediction model. In machine learning-based systems, learning models are exploited for predicting application performance on the basis of prior knowledge. Therefore, these systems are based on a performance-centric approach, and it is possible to talk about informed performance improvement. The main limitations of this approach are related to the higher computational costs compared to analytical-based systems and the need of a representative dataset for training the prediction model. What we can say in general is that machine learning techniques are more suitable for optimizing the execution of data-intensive applications in the context of high-performance computing systems. The main related works belonging to the analytical-based approach, which are focused on the Apache Spark platform, are listed in this slide. All of them tune applications according to information collected at runtime, but they focus on different aspects. Like for the first system is about choosing the serialization strategy for caching RDDs in main memory based on previous statistics collected on different working sets, including memory footprint, CPU usage, RDD size, and so on. The second work is about dynamically adapting resources to data storage using a feedback-based mechanism with real-time monitoring of the memory usage of the application. The third work listed here is about scheduling jobs by adjusting dynamically concurrency through a feedback-based strategy. Our IIWM approach differs in two main aspects from all these related works. First of all, our solution exploits a regression model to estimate a set of information about a running Spark application, using it to optimize in-memory execution. The second main difference is that it is trained offline, achieving fast and accurate prediction when used for inferring the resource demand of each task in a workflow. For what concerns the second category of related work, so the ones belonging to the machine learning-based techniques, we have some different approaches that have been proposed and exploited. One is the use of collaborative filtering. So in practice, what we have in this kind of work is the extraction of profiling information from a submitted application, and this information are used to feed a classification engine whose output is then used in a greedy scheduling strategy. This was one of the first works in this area. Another approach is based on game theory. Here we have that the task collocation problem is modeled as a cooperative game. And then we have another approach we can call mixture of experts, which the behavior of a Spark application is modeled by different regressors. Then at runtime, an expert selector is used to choose the best of the models. Also here we have some differences between these approaches and our solution. Our solution differs basically in three main aspects. First of all, it is specifically designed for data-intensive workflows. It also uses high-level information for describing an application. And finally, it is not restricted to application whose memory usage is a function of the input sites. So let's go through to an introduction of our system, which is basically made of three main steps, which are execution monitoring and dataset creation, prediction model training, and workflow scheduling. The first step is a step in which, starting from a given set of workflows, we generate a transactional dataset by monitoring the memory usage and execution time of each task in those workflows, and also by specifying how it is designed and providing a short summary, summary information about the input. The second step is the prediction model training, in which we start from the transactional dataset of executions and we build a regression model in order to fit the distribution of memory occupancy and execution time according to the features that represent the different tasks of a workflow. Finally, the third step is the workflow scheduling, where we take into account the predicted memory occupancy and also the execution time of each task as they are provided or predicted by the training model, and the available memory of the computing nodes that is going to be used in order to schedule tasks in the best way. In practice, we use this scheduler to control the degree of parallelism in order to minimize the risk of memory saturation. So if the scheduler is able to foresee that by using, for example, by executing 3 tasks in parallel, there will be a memory saturation event, the scheduler will try to avoid this situation, for example, by postponing the execution of one of these 3 tasks. I will describe this later with some examples. In the next slides, I am going to provide a detailed description of each of the 3 steps. We can start with the first one, which is about execution monitoring. Sorry. Okay. So this step, as I said before, consists of monitoring the execution of different tasks on several input data sets having variable characteristics in order to build a transactional data set on which we can train the regression model. As a test bed, we employed Apache Spark 301, And we employed the well-known MLlib library, machine learning library, available in Apache Spark, which covers the main classes of data mining tasks. In particular, we focused on the algorithms listed here, so decision tree, naive bayes, support vector machines for supervised learning, k-means and Gaussian mixture models for unsupervised learning, and FP growth for association rule mining. We started from a set of real data sets, and then we increased this number using an oversampling technique based on correlation analysis. The execution monitoring was done using the Spark REST APIs, which provide a way to access this information. So they expose executor-level performance metrics, which are collected in a JSON file. Then collected metrics are exploited. They include, for example, peak memory occupancy for both execution and storage memory, and also execution time of each task. So all these information are included in the transactional dataset. The second step is dataset creation. Practice using the API that I mentioned before, we monitored the execution of several machine MLlib algorithms, the ones listed before, on different input data sets. And at the end of this process, we were able to create a data set for the regression model training, which contained a number of information. In particular, this data set includes the description of the task, such as the class of operation it performs, like classification, clustering, and so on. The type of task, like, for example, fitting or prediction task, the specific algorithm executed by the task, like SVM, k-means, and so on. Then it also includes the description of the input data set in terms of number of rows in the data set, number of columns, whether or not there are categorical columns in the data set, and also the overall data set size. And also the peak memory usage, including execution memory usage and storage memory usage. The difference between the two is that execution memory is the part of RAM which is used for keeping the program, the task, whereas storage is the part of memory, so of RAM, which is used for keeping the data set or the representative RDD of the data set in memory. So we have peak memory usage, execution time, and these two, peak memory and execution time, also represented three, because peak memory usage is for execution and storage. So these three values represent the three target variables of the regressor. So the regressor tries to predict these values. In order to obtain more significant data, the metrics were aggregated on median values by performing DNX, if I remember well, 10 executions per task. This table is just a sample of the training data set. So you can see just a few rows from the transaction data set. So you can see which are the parameters you can find inside it. So the third step is prediction model training. Here, we decided to use, after many tests, our choice was on the use of an ensemble learning model, because this is very likely the best way to fit the nonlinear distribution of the features. The resulting regressor was built using the stacking technique. Is a two-layer model composed as follows. We have a first layer consisting of three regressors, gradient boosting, ADA boost, and extra trees, in order to grasp different aspects of input data. Whereas the second layer exploits a single decision tree regressor and is meant to predict the final value starting from the concatenation of the outputs from the first layer. After training 20 models that were initialized with different random states, we selected the best one by maximizing this objective function. The goal of this function is to choose the model that best explains the variance of the data while minimizing the forecasting error. In practice, this function jointly considers the adjusted determination coefficient, this one. This coefficient guarantees somehow more robustness with respect to the addition of useless variable to the model compared to the classical R2 score, and the mean absolute error normalized with respect to the maximum. Thanks to the combination of different models, the ensemble technique has proven to be very well suited for this task, leading to good robustness against outliers and a high forecasting accuracy, as shown in these figures that compare ground truth and regression estimates. In different configurations, you can see the lines about regression estimates and ground truth as basically almost always one over the other. So there are no visible or very few visible differences between the two curves. These results are detailed in the table, which shows the evaluation metrics for each target variable, including the R2 score and the Pearson correlation coefficient, Pearson correlation coefficient, the last column here. Values very close to 1 indicate a very strong correlation between the real and the predicted values. So we can see by this column that predictions in terms of storage memory, execution memory, and duration, which are the three target variables, are very, very accurately estimated by the prediction model. So after we have the predictions, we can exploit those predictions for implementing the workflow scheduling strategy. We decided to model the scheduling problem as an offline bin packing problem. Bin packing is a well-known problem widely used for resource and task management or scheduling in a wide set of application areas. And a formal definition of this problem is here, reported here in this box. So let n be the number of items, wj the weight of item j, and c the capacity of each bin. So the goal is to assign each item to a bin without exceeding the capacity c, and at the same time minimizing the number of bins that are used. This is a problem that notoriously is NP complete. Sorry, I have some, okay. That is NP complete. We, of course, made some adaptation of this problem to the purpose that is task scheduling. And in particular, we made these modifications or adaptations. In our context, an item is a task to be executed. A bin identifies a stage, where a stage is a set of tasks that can be run in parallel. So if we have, for example, 3 tasks in the same stage, this means that all these 3 tasks can be run concurrently on the given node. Then we have that the capacity of a bin is the maximum amount of memory available in the computing node. And finally, sorry, I have some problems with my mouse, so it's going to move the presentation without my intervention. Okay, sorry. The weight of an item is the memory occupancy estimated by the prediction model. Then we have also some additional constraints which are included to take into account the dependencies present in the workflows. So we have that all the workflow tasks have to be executed, and the assignment of a task to a stage must be in line with the workflow dependencies. So if we have that task Ti precedes task Tj, then the stage to which Ti will be assigned will precede the stage to which Tj will be assigned. So this is a short description of the scheduling algorithm. All the details are present in a paper that I will mention at the end of the presentation, so please consider that this is just a simplified version of the actual scheduling algorithm, but I will shortly describe this version. So in practice, what we do is, in a first step, we assign a weight to each task by using the regression model. So based on the estimates made about memory occupancy of each task, we assign the weight to the tasks, and the weight will represent, of course, the memory occupancy. In the second step, we sort the task list in descending order of weights, and this is the first fit decreasing approach. In the third step, given a ready task, so a task that has no existing dependencies, or no active dependencies, we find the candidate stage it can be assigned to. So if any stage exists for the task, we create a new one and assign task T to it. In case there are one or more candidate stages, we select the stage that has the lowest expected increase of execution time before the assignment of T. Then at step 4, we unlock all the tasks that depend from T, so they become ready to be assigned in their turn. Then at step 5, we repeat until each task has been assigned to a stage. After this iterative procedure, we have an additional step which we called the consolidation step. In practice, here, for each stage containing tasks with a 0 out degree, we merge with a subsequent stage if the available capacity is not exceeded. Finally, we have a scheduling plan, and we return it as a list of stages to be executed in sequential order, where each stage includes a set of tasks that can be executed concurrently. So we experimentally assessed the effectiveness of IIWM using, as I said before, Apache Spark 301. And in particular, we generated 2 synthetic workflows for analyzing different scenarios and different available amounts of memory. And we also assessed the benefits coming from the use of our approach using a real data mining workflows as a case study taken from a previous work. Without going into much details, in practice, we evaluated the ability of IIWM to improve application performance, taking into account two different aspects, which are execution time and disk usage. Okay, in practice, regarding execution time, let M1 and M2 be the make span for two different executions. If M2 is lower than M1, we can compute the improvement on make span by, using this simple formula, which calculates the percentage of improvement. Okay. And of course, the ratio between the two. Regarding the disk usage, okay, this formula in practice says that we are going to consider the sum of all the amount of memory used on disk with different configurations, and we compare this disk usage in case we are using IIWM with the case in which we are not using IIWM, but the so-called full parallel approach, which is the one normally used by Spark. Okay. Firstly, we evaluated the approach against two complex syntactic data analysis workflows. On these workflows, the full parallel approach showed its limitations due to high degree of parallelism. So if you feed this workflow, for example, to Spark, Spark will try to execute all the tasks that are ready to be executed in parallel. And this will lead to memory saturation, data spilling to disk, and so a lot of overhead that results in, of course, disk usage, but also slow execution. This workflow, okay, I cannot provide the details about this workflow, but as I said before, there are details in the paper that I will mention at the end. This is a workflow with 41 nodes, data-intensive tasks, which include operations like classification, clustering, and so on, that are linked together via some dependencies, which are here represented as these arrows, of course. And the first step with this workflow was to predict the memory occupancy and the execution time of each task in the workflow. Actually, we assessed the accuracy of this process, and we verified that the regression model was able to accurately estimate the peaks on storage and execution memory and duration, as shown here in this table. So you see storage memory, execution memory, and duration are very well estimated with very low errors and strong correlation, Pearson correlation between real values and estimated values. The table below compares the performance of the full parallel approach, which is the standard Spark approach, with our IIWM approach. As we can see, oh my God, okay. The number of stages in case of IIWM is greater than the number of stages in case of the full parallel approach, but the execution time is much lower. So we have just 21 minutes in our case compared to 31 minutes, which is 10 minutes less. And also we can see that with our approach, the disk usage is always 0, so no disk has been used. So 0 GB, no writes. Whereas if we look for the full parallel, we see that the peak disk usage was very large, and the amount of time spent doing writes was also significant, so we have 11 minutes, and so on. Of course, when the memory size, these values are obtained using 14 gigabytes of RAM. And of course, if we increase the amount of memory available in the server, the full parallel turns to be equivalent to our approach. But of course, in general, the amount of memory is not unbound. But anyway, we show in the two figures below that when we increase the amount of memory available, so we pass, for example, from 14 to 30 gigabytes of RAM available, the two strategies become equivalent. So this is a result that is well expected, of course. This is the second synthetic workflow. It's smaller, so it consists of 27 tasks. But also in this case, as shown in the top table, the regression model was able to accurately estimate the peaks on storage and execution memory, and also duration. The second table compares the performance of the full parallel approach with our IIWM using 9.5 gigabytes of RAM. We have less RAM because the tasks are smaller and the workflow itself is smaller than the previous one. But also in this case, we see that our approach increases the number of stages, so the number of tasks that run in parallel is lower, but the execution time is lower as well. So we are able to save about 7 minutes. And in this case, we have some disk usage also in our approach. In fact, we try to minimize the disk usage, but in some cases, it's not possible to avoid some data spilling, but the amount of data spilling is much lower than the full parallel case. And in this case, we included the two figures here, and that show the disk occupancy during the execution. So we monitored over time the amount of data being used by the system. And so we see some peaks here in the case of full parallel. So there is almost always some data spilled on the disk, whereas in the case of IIWM, we have just one time in which data are spilled on disk, and also the amount is much lower. You see, it's just less than 1 gigabyte, 0.3 gigabytes, compared to more than 25 in the peak of the full parallel approach. So even if we are going to write something, this is much lower than the amount that's being written by the normal scheduling strategy. Okay, in order to assess the performance of our approach against a real case study, we used a data mining workflow that implements a model selection strategy for the classification of an unlabeled dataset. This figure shows a representation of the workflow that was designed by using the visual language VL for cloud. In practice, we have that the training set is divided into a number of partitions, let's say n partitions, and then we have k classification algorithms that were fit on each partition, in this way generating k times n classification models. These k times n fit models were evaluated by a model selector on a test set to choose the best model. Afterwards, the n predictors use the best model to generate and classify datasets. And the following K classification algorithms provided by the machine learning library of Spark were used. We used the C4-5 algorithm, which is in a decision tree algorithm, support vector machines, and naive Bayes. Okay, this is a short description of the workflow. I hope it was clear enough, but in practice, in this scenario, the IIWM can be used to optimize the data processing phase, which is about the execution of the K times N classification algorithms. The other phases, which are data acquisition, data partitioning, were outside our interest, so they are not optimized. And the red box here, this box, shows the tasks of the workflow that we focused on. The table below shows that with our approach, we were able to save about 40% of the time, passing from 11 minutes to about 7 minutes. And by passing from 2 stages to 3 stages, the disk usage is completely voided. So in practice, whereas the full parallel approach is going to use more than 100 gigabytes during execution, with more than 9 minutes passed making writes on disk. Our approach had 0 gigabytes used, 0 minutes writing, and so on. So it is a significant performance improvement compared to the full parallel approach. These are some figures from the previous example. So the top figure shows disk occupancy over time. You see here, this is disk occupancy in the full parallel case, and this is disk occupancy in our case. So always 0 compared to a disk occupancy that reaches 125 gigabytes at the end. And of course, this curve ends before this curve, because here the execution time terminates. And the 2 figures below, as usual, show that if we increase the amount of memory, of course, the 2 strategies tend to be equivalent. So I am going to provide some conclusions about this work. We proposed this intelligent in-memory workflow manager in the context, meant to be used in the context of data-intensive workflows on HPC systems. We focused on data-intensive workflows because data-intensive workflows are going to be more and more important in many application areas, from scientific computing to data analysis in social network, medicine, and a lot of cases in which huge amount of data are available. And so data-intensive workflows are the best way to represent the complex applications in all these areas. And so given the interest in the use of in-memory execution systems, Spark is perhaps the most important system in this area, but there are other systems which are based on the same approach. We focused on trying to optimize the use of these systems. So we made this by exploiting a machine learning model for estimating performance of tasks, and then a first fit decreasing strategy for task scheduling. The main benefits of this system have been assessed in different scenarios characterized by a high-level parallelism and a limited amount of memory reserved for execution. And we also checked what is the behavior of the system when this amount of memory changes. The results that we obtained on both synthetic and real data mining workflows using Spark are very promising, but of course there is room for future work. We will investigate aspects like the presence of other common stages in workflows besides data analysis. Also the use of more complex algorithms like artificial neural network or random forests. And we can also try in the future to take into account other information about tasks, input data, and also hardware platform features to go beyond the idea that the system is fully homogeneous, as I said before. Okay, thank you for your kind attention. And this is a reference to the paper, to a recent paper in which we describe all the details about this work that it was actually very difficult to explain here. So I hope you can, if you're interested, you can find the details there. And I also take the opportunity for thank the Vidyavardhaka College of Engineering for virtually hosting me today. Thank you.
Thank you so much, sir. So any questions from the participants? So if you have any questions, kindly drop them in the chat box. Right, sir. So we've got no questions. So I, on behalf of the Department of Computer Science and Engineering, VVCE, I extend a heartfelt thanks to Dr. Paolo Trunfio, sir, for delivering such an informative session. Thank you very much, sir.
Thank you. Thank you very much for your introduction and for your hospitality. Thank you.
Thank you. I wholeheartedly thank all the participants for attending the session. The feedback link will be posted in the chat box. So thank you all.